Thank you very much for the opportunity to come and give this talk today. I'm Jen Heldmann from NASA Ames and the SETI Institute, and I'd like to acknowledge the other people that are on this project, because this is part of the core team for this idea that we're coming up with and trying to work through. Brian Day from the Education Division is here in the audience, and Liza Coe is also from Education. Pascal Lee and Chris McKay aren't here today because they're back at NASA headquarters for a different lunar meeting, so they couldn't make it today. But Jeff Moore and Michael Sims are here as well, so we have a good representation. We can hopefully answer some of your questions. And what we're going to talk about today is an idea for the Lunar Database and supporting lunar landing site selection for NASA's upcoming return to the moon. And just to put this in context for the reason why we're doing this, just give a little bit of background information. This all stems from NASA's vision for space exploration. And so this document was released in February of 2004. And so NASA is now working very hard to realign with these objectives that are outlined in the vision for space exploration. And some of these objectives include retiring the space shuttle by 2010, so just a few years from now. And the shuttle flights that go from now until then will be aimed at finishing up to the best that we can the International Space Station and honoring all of those international commitments that we have. The parts that we're interested in for today are NASA's plans to conduct a series of robotic missions starting no later than 2008 as human precursor missions, so basically gathering the data that we need in order to support future returns of humans to the moon. And simultaneously with that, NASA's also developing the Crew Exploration Vehicle, or the CEV, and this is the vehicle that will be taking the humans to the moon and to Mars and wherever else in the solar system that we go. Because the goal is to have human missions to the moon by 2020, and we're going to the moon first as a stepping stone onto Mars, so that's the next bullet in the whole grand plan. So that's the overall scheme. But focusing in on the lunar missions that are going to be relevant for the data we're talking about today, these are the upcoming missions in the new exploration program. In 2008, we'll be launching the Lunar Reconnaissance Orbiter, and that's shown over here. So this is a nice mapping mission, which will take a lot of data with several different instruments. Also, on that mission, which was just decided a few weeks ago, there will be a secondary payload on that launch, and that's the LCROSS mission that's right here. And that's a mission that I'm working on, and basically what we're doing is we're taking the upper stage of the launch vehicle and attaching this little shepherding spacecraft to the end of it, and then driving both of those entities to the moon. And then once we get close to the moon, we separate the upper stage of the launch vehicle, which by now is just a big piece of metal, basically. And then we have the shepherding spacecraft. And the big piece of metal slams into the moon at the South Pole, ejects a big plume of dust and whatever other material is in there. And then the shepherding spacecraft flies through that plume, makes a lot of measurements, returns a lot of data, and we're going to try and figure out what the regolith is composed of, and also the reason we're interested in going to the South Pole region, we'll talk a little bit more about this later too, is because these are regions in permanent shadow, and we think that there might be water ice there, so our main objective here is to go and see if there's water ice in these permanently shadowed regions at the pole. So that's the LCROSS mission. And those are both launching 2008, and then after that, our plans for a series of additional missions, several lunar landers that are being studied right now, and this is all leading up to finally human exploration 2018-2020 timeframe. So the reasons that we're going back to the moon, what we're actually going to do once we get there. First, preparation for human Mars exploration, because we're using the moon basically as an analog for Mars, and we're learning how to live and to work off of our home planet. So there's objective 1, and objective 2 is scientific research on the moon, so we can actually learn something about our satellite. And also we'll be doing scientific research on Mars as well, so it's relevant for doing this on the moon. And we go to the moon for 2 main reasons. It's a high-fidelity analog that have real risks and relevant challenges. So it's the best place that we can go, and it's nearby where we can actually test out what we're going to be doing once we go to Mars, which is a much more difficult problem. And also, we actually need to build up experience in long-duration and remote mission operations, so how we're going to actually conduct these types of missions. So we're going to practice that on the moon first. And I'm not going to run through each of these bullets, but there are good, valid reasons that a lot of people have come up with for how the moon is preparation for Mars, in terms of establishing long-term bases, in terms of the science that we'll actually do, geology, biology, chemistry, et cetera, doing that field work, the needs that we have, like long-term life support, that we're going to need for both of those types of missions, technology flow-throughs, and how we actually do these operations, and also human performance issues and psychology issues and group dynamics and individual performance and things like this. So the reason that we're so interested in the moon, and there's a very close connection to the moon with NASA Ames, because NASA Ames is the home to the Robotic Lunar Exploration Program, or the RLEP office. And the goal of RLEP is to conduct these precursor robotic missions in support of human returns to the moon. So Ames is, for the entire agency of NASA, is heading up this entire program. And all the data that's obtained from these robotic missions and from all the previous lunar missions that we've had, I'll go over some of those, have to be cataloged and made accessible to the community so that they're actually useful. And that's not the case right now, and that's something that we'd like to change. And we're going to use this data to guide site selection activities to determine the location of future landers that we're going to send to the moon, and also where we would set up crewed bases on the moon, because we don't actually have those sites picked out yet because we need this precursor data to make those decisions. So the real underlying thread through all of this work is site selection and figuring out where we're going to go on the moon. And site selection drives the lunar program in the near term and in the far term, because long-term planning, we have to define what we're going to do on the moon, and that's dependent upon where we go. And that helps resolve the architecture for the types of missions that you're going to send, if you're having a long duration mission versus shorter duration missions, and what you can do in each of those time frames. And for the near-term planning, we're generating target lists for the places that we want to take data for the Lunar Reconnaissance Orbiter, which launches in 2008, and also for future mission lander objectives, depending on where we end up going and what information we decide that we need. So we have been to the moon before, and we've landed on the moon, and here's just a little graphic showing where we've been. So we haven't been to the far side at all. We haven't landed over here. Here's the near side, because the same face of the moon always faces towards the Earth. And so most of the landings have been focused in the equatorial regions. We haven't sent anything to either of the poles, and this will be a significant, so that's where we're sending the L-Cross mission as well. So there's been a lot of interest in what's actually going on at the poles of the moon, because we haven't actually been there. So what I want to do now is quickly just step through the considerations for site selection and show you the types of data that we need to support these decisions. And the considerations that we've outlined here, we have 8 different categories. The general accessibility of the landing site, basically based on orbital mechanics, can you actually get there? Landing site safety, once you've picked your site. Mobility, so once you get there, can you move around, and how well can you move around, and how far? The utility of a site as a Mars analog. Power considerations, if you want to have in situ resources to generate power. Also communications, that's referring to communications with the Earth. And ISRU considerations, in situ resources, and geologic diversity for science. And so basically what we do is we go through each of these categories and figure out which sites are best and optimal for each of these, and then we have to synthesize all that information together and see which sites end up being the best overall, considering all of these categories. So the first 4, we've grouped these together: orbital mechanics, landing site safety, mobility, and Mars analog. Because these first 4 really can work anywhere on the moon. There's no place on the moon that you can't go to. For example, orbital mechanics, NASA has said, we're going to use a big enough rocket, you can go anywhere on the moon you want, so don't worry about it. So that one's done. Landing site safety, these are really, we're talking about local versus regional changes. So in this little schematic here, which is very simple but very poignant, obviously if you're picking a region of the moon, you're going to land in the flat part. You don't land on the pointy rock over here. So this is local scale variations. So you don't just get rid of one part of the moon. It's not like you can't go to the North Polar region because there's nowhere to land, or you can't go to the eastern part of the moon. You can go to any region, you just pick the flattest part that's in that type of terrain. Also, same thing for mobility. That's more of a local scale variation, so you don't discount any large regions of the moon for that, so you drive your rover in the flat part and not over all the big rocks over here. And same thing for a Mars analog, because we're learning to work and live off of our planet, and we can do that anywhere on the moon. So there's no regions that we really are better than any other ones. The next one, though, power and light, this one actually does matter, because there are certain regions indicated up here by green at the poles where there's near permanent or permanent light at the rims of craters. And this is very important because if you want to use solar power, say, to power your base or your rover or whatever spacecraft you've sent up there, you might want to go to one of these regions of near permanent sunlight. And it's only at the poles because the Earth is rotating around its axis, and these are the regions that are in continuous light. And we'll talk about as well, these are also regions where there's continuous shadow, where the ice might be, which are down inside of the craters. So you've got the crater rim at the top with the light, and then the crater in the darkness at the bottom. And so you could go to the near side or the far side going to the poles. And this is a little misleading because these areas aren't actually this big. They're much smaller and much more localized, and we have that from imagery data taken over long time frames. For communications, again, because the moon always shows the same face to the Earth, because the period of rotation is equal to the revolution period of the moon, so that's why it always looks this way. You can go anywhere on the near side, and you can always look at the Earth and have direct communications. If you go to the far side, then you're going to have some sort of comm relay system or some other satellite system in order to relay back to the Earth.
Nearest crater near a pole, does being near a crater automatically imply a hazardous landing site?
Repeat the question.
Yeah, the question was, is going to one of those craters near the pole automatically make you in a hazardous landing site? And the answer is we don't actually know, because there are flat regions. Well, all the craters are different, but it depends on the terrain of that particular crater. And so people have argued for and against going to cratered sites, because at the poles, particularly at the South Pole, there's a lot of jumbled cratered terrain. So I've heard it argued that you don't want to go to this region because your mobility will be limited, because not only the terrain that's difficult, but also the lighting conditions are difficult, because it's changing a lot at the polar regions. If you're here at the equator, it's 14 days of dark and 14 days of light on the moon, so it's a whole different type of scenario. But for the topography, that also changes as well.
With that change in lighting, wouldn't that make it a really great opportunity to get topographic information? You have shadow all sorts of different directions.
Yes, and that is one of the best ways that we can get topography. Oh, the question was, with the changing shadows, can you get topography? And the answer is yes. And we're also going to get better topography because we're sending a laser altimeter on the Lunar Reconnaissance Orbiter, so that will give us even more precise information, because we don't have very good topography at the poles, actually, and there's a lot of uncertainty in the heights. So. This we've already talked about a little bit up in the cratered regions at the poles. This is where we think that there may be ice in those permanent shadows. So if there is ice in these permanent shadows, we need to go there and find out if there is or not, so we can make a decision if we're going to use water ice for ISRU, which is the in situ resource utilization. And so this will be one of the objectives of the LCROSS impactor mission that impacts into one of these craters and ejects all this material up into a plume that we then fly through and we observe from the ground to see what's going on in these permanently shadowed craters. But using water ice isn't the only resource that we could use on the moon. There's also, in the regolith, here closer to the equator in particular, where we know that there's oxygen in the regolith on the moon. So we may want to go and harvest the oxygen and use that as our in situ resource. And if that's the case, then you're going not to the poles, but you can see here's a map, titanium dioxide over here. So you can see you want to go towards the equatorial regions in the mare over here instead of at the poles. So it depends on the abundances, what we find, how hard it is to extract this material, but we need more data in order to make this type of decision. Then another consideration is the geologic diversity. And so these numbers just represent a list of different sites that geologists have put forward as saying these would be good sites to go to on the moon to study because they're really, really interesting. And one of the best places to go is up here in the northwest quadrant of the moon. And Jeff Moore's in the audience as well, and he can talk to you at length about why that's so. But there's a lot of geologic diversity here. There's mountain ranges, there's volcanic flows, geologist paradise is what I've heard it called. So if you were going just for purely scientific reasons, you might not particularly want to go to the poles, you might want to go somewhere over in here. So there's different considerations to be put forward. So we have all of these outstanding questions, and we have decisions that need to be made to drive the upcoming missions that are coming. So a need that we've identified is the need for something like a lunar database, because there needs to be some way for the community to access all of this data that we have from previous missions. So we need a user-friendly interface to disseminate this data, hopefully via the internet so that the widest amount of people can use it. And what they will use it for is to support site selection and surface operations of these robotic and human missions. Public outreach would be a great public outreach tool as well, and used by the scientific community to do lunar research. So just a quick overview of what types of data do we have and the types of things we would like to integrate into this large database. I'll just step through briefly some of the previous missions to give you a sense of the information that we have already. This was Ranger in the 1960s, and this spacecraft deliberately crashes into the moon taking pictures as it's going down. So you can imagine you have a whole set of nested images as you're approaching impact. And so you have several thousand images from these 3 successful Ranger missions. And so here's an example of some of the images that you would have. And this also highlights the fact that you have the actual data that came back from the spacecraft. Then you also have data products that are generated from this raw data. So there's a decision to be made as to, we'd like to have all of the raw data accessible, and then which of the generated data products do you also include in this database, which would be useful, such as rendered terrain maps from that. Next up was Lunar Orbiter, later in the 60s. We've got a few thousand images from this. There were 5 successful missions. The first 3 were going around the equator and looking at potential sites for Apollo. And then the last 2 were in polar orbits. We're doing more broad-scale regional mapping. And so about 99% of the moon was mapped at a resolution of about 60 meters or better. So we have a good idea of the terrain for most of the moon. Next up was the Surveyor missions. Following this, you can see that there are a lot of images that have been generated from this. We had 5 successful landers. They had television cameras and strain gauges as they were coming down and landing, which is interesting. And then as the missions progress further out, you include different instrumentation on these different missions. So here's just here's the first image that we had, and then you can mosaic these images. So this would be another one of the data products, depending on how you wanted to present the data. And of course, there's Apollo. And there's a tremendous amount of data from Apollo, which we couldn't even have time to talk about in a 1-hour lecture. But some of the imagery, we had the metric camera, covered about 20% of the moon, 25 to 30 meters per pixel, which isn't so bad, so a little over 7,000 images. There's also the panoramic camera, which covered at about 1 to 2 meters per pixel, which is pretty good. So that's over 4,500 images. And then there's also some handheld photography, which sent back a lot of images, nearly 20,000 images that are in there. And so you can see that there's images of all different sorts of things. Here's outside of the spacecraft looking. Here's on the surface with the lunar rover astronaut. Here's looking at spacecraft in space. Here's pointing, there's a lot of images pointed back at the Earth, which is very interesting. And then also, especially with the handheld photography, there's a lot of pictures of the astronauts in the spacecraft and whatnot. And putting this slide together took me far longer than it should have, because I just started going through all of those images because it's really fascinating. So there's a lot of other science that was done on these missions as well, and I'm definitely not going to read through all of these different experiments that were on here, but this is just to give you a sense of the vast amounts of data that we have that would be nice to be made accessible to the community. You can see as the missions progressed, we have orbital and surface experiments, and the number of experiments and the complexity of them increases. So these data sets do exist, but they're just not very accessible right now. Further out back in the 90s, Galileo was actually going to Jupiter, but on the way it took some images of the moon. So here's some images that was taken down here. Here's a little portrait of the Earth-Moon system, which is nice. And also collected spectral data, which is the background image in here. So this is a false color image, obviously, showing different compositional differences. So we have spectral data as well that would be nice to be able to use. Then Clementine in '94 had several cameras in several different wavelengths, returned nearly 1 million images, so there's a lot of data out there at all these different wavelengths. And also there's topography mapping with laser ranging, so that's useful as well. Lunar Prospector was a very good mission. This is one of our last missions that we had. This was run out of NASA Ames, and it was in '97. It didn't have a visual camera on it, but it had gamma ray and neutron spectrometers, alpha particle spectrometers, magnetometers, etc. And the really interesting thing that came out of Prospector was the discovery of these water ice signatures. There's a spectrum down here, and you see that there's potentially hints for water ice down at the poles. And so these blue spots are showing where the water ice might exist in these permanently shadowed regions. And so what we're seeing really are enhanced levels of hydrogen. That's what we're detecting. And we inferred that this could potentially be water ice. And it's only at the 1 to 1.5% level, so it's not clear that it absolutely has to be water ice, but it might be. And so since water is such a valuable resource, if we find it on the moon, that we might want to utilize, that's why there's all this emphasis and focus on really understanding the poles, because we haven't really sent spacecraft there and actually ground truthed it before. So the idea that we're coming up with, an idea for a joint NASA-Google project, is to have a partnership to develop and maintain a lunar database and website. And the purpose of this would be to distribute the lunar data and certain data products as well. It's It's really important that they're co-registered so we know where we're looking and some other things as well, in an easily accessible format to NASA, to other researchers, and to the public. And the purpose of this would be to support NASA site selection activities for future robotic and human landings. So I don't think it's too far out there. I think it seems like a pretty natural fit. Here's one of the quotes taken from when Ames and Google were announcing all these ideas to work together and whatnot. So the vision that I have is sort of like a Google Earth, but for the moon, and with additional capabilities as well. So some of the things that would be really neat to have that our team has come up with, characteristics we would really like to see, visualization with full zoom capability, so you can go into the highest resolution data for whatever site you decide to pick. A clickable map, so you can look at other co-registered data sets as well. So it would be really nice to take all the data that we have and bring it all together in one place. So temperatures, elevations, sunlight availabilities, composition, radar signatures, the hydrogen content, that's a big one, gravity fields. Slopes are important for landing sites as well. You can't land on a cliff face. Surface roughness, that's also important for landing sites. And it should be searchable so that you can search any data field as a variable, so you can find whatever it is that your heart wants to see. And then other requirements as they come forward, 3D representations or any other things that would be useful in presenting the data. So some of the objectives that we've come up with our team, and these are all just tentative, so we're just, this is our brainstorming sessions. Open public access to all the lunar data that we have, including data from the past missions and also the upcoming missions that are coming, so the new data as well. Easy, reliable, and timely access, so it has to be user-friendly. Maintained access, so we don't want it to atrophy. This is one of the problems with all these earlier missions that we've had for the lunar data. You can't just go out and search online right now. You just can't find it, and it's very difficult to find. And we have projects right now that are going on where we're digitizing some of that older data so that it can be accessible to more people. Complete traceability of the data's pedigree. This one's really important because we need to know exactly what processing was done on any of the data that's put into this database if it's ever to be used by the scientific community, which I think would be a nice thing so that it's actually a useful product to have. So we need to know if it was co-registered or not, if it's been radiometrically calibrated. Whatever processing has been done on the data needs to be documented in here. And this feeds into having data and the data access consistent with scientific uses, again, so that it's a useful product that we can use. Having a straightforward pipeline of designated data onto this site so that it's easy to get data from all of the upcoming missions that are coming so we can get that in a timely manner. And also including the scientific community on aspects of the lunar data. So we don't want to just leave some of the users in the dark. We'd like to get input as to what would be most useful in developing this product so that we can actually use it later on. So we've outlined some potential tasks. And again, these are just tentative, so these are just our thoughts, completely open to comment and suggestion. So NASA Ames already is leading site selection and supporting surface activities, and that's a natural product of the fact that the ARLEP office is based at Ames, so Ames has a heavy hand in the lunar exploration game at NASA. Provide oversight on the quality of the data products, so again, to make sure that it's useful for the community to use for these site selection and surface activities. Providing access to the raw and processed data products. So we have a project going on right now being led by Michael Sims, who's here, so we can answer more questions about that, to bring all of this data together in one co-located place. Because right now it's scattered in many different places and not accessible. So we're trying to bring that together, and the idea is that we go through NASA and take all the data that we have, and then we have this database that we can deliver to Google, and then have that put into a more user-friendly format. And also we can provide data analysis and interpretation expertise because we have a good lunar science base at Ames, so we can help with interpretation of what's going on. And also the data analysis is important as well because you have to know how to deal with the data and how to process it, and it's not always such a straightforward thing. Potential tasks for Google: develop the website, so maybe something based on the Google Earth model would be really nice. Incorporate the previous mission data, so hopefully getting that to you in a digital format, so Lunar Orbiter, Apollo, everything that we've already stepped through in all those different data sets. And also provide a mechanism to incorporate future data. So we have LRO that's launching, we have the LCROSS mission, we have a lander mission that's in formulation, RLEP-2. So some way to include all of this data in that database. And then create standard and requested co-registered data products. And co-registered come up a lot because it's pretty important. So there's clearly expertise at Google that NASA can benefit from, and it would probably be a good idea if NASA did benefit from that. Obviously, large-scale data management, Google's the place to go. Data mining, I don't have to tell you guys this because you guys are the experts. Introduction of entrepreneurs to the space agency, web interface development so that it's user-friendly, and bringing this information and the excitement of exploration out to the public in the US and abroad. Easy access to the data and data products for NASA and other users that would like to use it, and low-cost solution to database management because we have all of this data that we need to deal with. NASA can also bring something to the table, I think. We have the access to the lunar data, so that's why we're trying to collect that now and get that all together. Development of the software to process that raw lunar data into calibrated data products to make it actually useful for people to look at. We have the scientific expertise to interpret the data with our good base of lunar scientists, some of whom are here today. And also the lunar exploration program that warrants the necessity of having this lunar site selection catalog in the first place. So there's actually a reason for doing it other than just it's cool and a neat thing to do, but there's an actual real reason to support these future missions. And then also sharing this information and the excitement of exploration with the public. And then there's some mutual NASA-Google benefits as well. Strengthening ties between NASA and Google as Google enters into the research park over at NASA Ames. A way to initiate public and private partnerships, and provides a nice project to start building relationships for future projects as well that could be beneficial to both sides. And also bringing space science and information technology benefits to the general public. So we want to get more people involved in understanding and appreciating the excitement of we're going back to the moon and we're sending people to the moon and then we're going to send people onto Mars. And it's a really spectacular thing, and getting the word out is something that Google does well. So we've done a quick estimate just to give you an idea of how much data we're talking about. We very roughly estimate about 50 terabytes of lunar data exists from the previous missions that have already gone. And then we also have the upcoming missions as well that would have to be built into that database. So just a quick summary, we actually need a consolidated lunar database. And it has a reason for supporting these missions. And they'll have other uses too, science, community, public outreach, et cetera. But we think it would be a nice idea for a joint NASA-Google project to develop this user-friendly database for all the missions with raw data, data products, et cetera, et cetera. So I'll just leave this information up here. This is our contact information. You can call or email. These are the core members of the team that are up here now. And I'd be glad to take questions and ideas.
How much access does NASA have to like missions from other countries like Russia and the ESA? The missions that they've had, they might have collected some lunar data. How much access to that data do you have? And also, like India is having a mission in a couple of years.
Yeah. The question is, how much access do we have to international missions that have lunar data? And I think Michael can probably answer for the past missions, but for the upcoming missions, I know that NASA is in negotiations with other countries to have data sharing. So for example, Japan is launching a mission called Selene, and so NASA's in, talking, maybe we can cooperate, and share data, LRO versus Selene and that sort of thing. So I know that there's negotiations going on for future missions. Michael, do you have a sense for the past missions?
But it's on a case-by-case basis right now. But there's certainly a lot of interest in other countries that have missions to share the data.
And I know particularly the Indian mission that there are a number of our colleagues who are working with specific scientists in India to collaborate and work together. And we have the expectation that most of those data will be available to the international community, including, of course, the U.S.
Any other questions?
Schedule requirements? What's your schedule
Sorry.
requirements?
Oh, schedule requirements. Yeah, we didn't put that into our overall idea. The sooner the better, really. Because, but realistically, LRO is launching in 2008. And the initial plan was to have a lander mission, or have a mission every year through RLEP. But that schedule has sort of slipped a little bit. But we have to start site selection well before the mission itself. So a year. But there's no hard date right now. because of the fluidity of the RLEP schedule.
Yeah, so I was curious about your thoughts on how you would approach the outreach aspect of this. Do you view this as a one-way communication channel, or do you view this as something where users could, perhaps give, input their own ideas as to, possible interesting landing sites, or share information with other members of the public that they find useful?
Right, that's a good question. The question was the ability for having input coming from the public and whatnot. And I think that if we could do it, that would be useful, because for a particular example, with the LRO mission, the LROC, which is the camera that's on that mission, they're going to be soliciting for sites from the public to actually go in and say, I would like a picture of this site, but they haven't specified, I just met with them a few weeks ago, and they haven't specified the mechanism for doing that yet, for getting input from the public so that they can actually target the camera. And same thing goes for on the Mars mission that just went into orbit, the MRO, the high-rise camera, they're calling it the people's camera, because they're soliciting targets, from people that want to have specific regions on Mars that are imaged. So if there is a way to do that, I think that would be great. And I don't know of the protocol yet for doing that for, particularly LROC. So, but it would be very, very good. And it would be a very good way to get more, interest and interaction in that. So, but those are just my thoughts. It's not the official position of NASA. I don't know. Yep.
How encumbered is this data?
Sorry?
How encumbered intellectual property rights, et cetera, is this?
I believe it's public. It's public data. Yeah. Right.
There is a brief period right after data are acquired, but it undergoes verification. So these very short proprietary periods are often on scales of a few months at most. That is initially basically ground, but within a matter of usually never more than 3 months, it's all public domain.
So where did the that Google Maps database come from?
I don't know. I'd ask a Google person. Does anybody know?
See, Clementine data was collected in the 1990s, so it's all digital. And the U.S. Geological Survey invested a lot of energy in registering that data and registering also to a geodetic base, so it has good positional control, relative positional control itself. So therefore, it makes itself amenable to a global map product. But one of the things that needs to be done with these older data sets, like for instance, the Lunar Orbiter, which was collected in the 1960s, were analog data, and in fact, the archival data storage is on hard media, i.e., big images or negatives. So that can be scanned in, they'll have to be probably geometrically corrected and registered to a reference database, such as Clementine, and after we have this high-resolution topographic mapping activity from LRO, we'll have probably more or less absolute geodetic control, which will register all the data sets.
Right, and that's the digitization is a good point, because there's a project at Johnson Space Center that's being funded via NASA to digitize a lot of the Apollo data. And there's a proposal from a group in New York to digitize the Lunar Orbiter data, so we can get that in a format that's accessible from the original data sets, not second or third generation prints.
There are already 2 projects going on to digitize some level of fidelity Lunar Orbiter data. One at the U.S. Geological Survey in Flagstaff, and the other at the Lunar Planetary Institute in Houston, Texas.
Right, but I think they're all using second, third generation stuff.
They're using their master
Their
sets, but were themselves created from the archival sets which are back in Maryland.
So there's some digital data available. Okay.
I'm a little confused. What is this original data that's not digital? Are we talking photographic plates, or can you give a couple examples?
It's the hard media. Yeah.
Lunar Orbiter used technology that had been developed by the Air Force for surveillance in the early 1960s. How the system works, it created a giant Kodak, Polaroid camera system, which basically developed a big strip, 70mm strip of film on board the spacecraft, which was then scanned and passed an optical scanner, and an analog signal was sent back to the Earth and then scanned onto film. That's how they produced the image. So So for instance, even though people recorded tapes or analog tapes deteriorated, and the archival copies are those master negatives that were generated directly from the signal. We're talking about 1967, you know, so. I mean, it's amazing what they did. If you look at the quality of the images, they're strikingly good, so you think about how they got it, it's all the more amazing sort of ignorance and brute string technology people employed to do these things back in those days.
All right, anything else? Well, we can stick around for a few minutes afterwards if you have additional questions. But thank you very much for coming, and I hope we piqued your interest.